Welcome to the demonstration corner. This is part 2 to measure in small samples. Here we'll be measuring a very small sample of Macor ceramic, which is 5 millimeters by 5 millimeters by 1.3 millimeters thick. We'll be measuring that symmetrically, one on the bottom, one on the top. This is our MP-1 with various methods that are available. It's our marquee transient method. MP-1 stands for measurement platform. And this device we'll talk a little bit about. Of course, there are a number of other live demos that really go into depth of all the features and bells and whistles, because we put a lot of work into making this the leading instrument in our industry. Classic demo corner. Here we like to do a little loop with the camera to talk about multiple methods. In this time in our industry of making thermal conductivity measurements, there is an oversimplification of the measurements. Yes, convenience and speed is important to making measurements, but we put more weight on proper approach and proper consideration of methods to make sure that our customers are using the most ideal method. And if they're not, understanding the error associated with their assumptions of the method. That's important. So, going over to the very end, this is our HFM 100. If you go to the website, you can see a lot of the bells and whistles. There's multiple temperature ranges and multiple sample sizes, but this method follows ASTM C518 for measuring insulation and construction materials. This is our guarded version of that. This is called a guarded heat flow meter. This uses a guard furnace to isolate the in-plane direction, so it allows you to use a sample size of 2-inch diameter. The sample's thickness can change up to 1 inch thick. We have a proprietary mechanical movement component that allows you to measure from 0.1 watt per meter Kelvin up to 100 watts per meter Kelvin, and this can go up to 300 degrees Celsius. You can vary the pressure. It auto measures the thickness, so it's a very capable instrument. And again, this follows ASTM E1530. The MP-1, which we'll talk about in a moment. And here we have our TPS-2, which is our basic transient plane source, following ISO 22007-2. There's modules available with this to measure anisotropy, thin conductive sheets, and thin films. This has 2 thermal conductivity ranges of 100 and 500 watts per Kelvin, depending on your needs. And it has a number of automated temperature devices for measuring with temperature. We've tried to keep this one very affordable. That's the purpose of this method. This is our transient hot wire following ASTM 7896. The temperature range on this has a built-in temperature platform. This is a proprietary heating and cooling component of our instruments that are also incorporated into the MP-1. Thermal conductivity, thermal diffusivity, and volumetric specific heat for liquids and pastes. We did a demonstration of the MP-1 with transient hot wire, but this is an instrument uniquely designed for this method. This has the ability to go from cryogenic up to 300 Celsius, depending on your options you need. There are multiple ranges of temperature, and back pressure of 20 and 35 bar, and that is really critical for measuring past boiling points on liquids. And then down further, we have our small format heat flow meter. We designed that specifically because of the overuse of transient methods on highly heterogeneous materials. Of course, the key advantage of the transient methods are small sample format, but often values are overestimated on highly heterogeneous, especially insulative materials. So we designed a small format heat flow meter that takes 2-inch, as small as 2-inch sample size and up to 1 inch thick, for measuring very accurate thermal resistance and thermal conductivity of insulation. That's our HFM 25. And then down the end is the baby brother to the MP-1, and that's the portable MP-2. That combines asymmetric or single-sided transient plane source sensor, transient hot wire sensor, transient line source, all primary designed for function, smartly and economically packaged into the MP-2. This is a widely used instrument for entry-level testing and very capable. It just has more narrow range of function. So our MP-1, what we're going to talk a little bit about is measuring the bulk or average thermal conductivity, diffusivity, and volumetric specific heat for small format samples. We have radius of samples down 0.5 millimeters radius, roughly 0.9 millimeters radius, 2 millimeters radius. Why? Is because we want to cover the sensor diameter by at least 2 times the diameter. So in this case, excuse me, the Macor that we're testing is 5 millimeters by 5 millimeters. The instrument automatically suggests what sensor to use based off those dimensions, and we'll show that. So without much ado, I will say if you're interested in how our data compares to NIST available materials, we just did a demo video on NIST 8420, which is electrolytic iron. This is 6.4 millimeters radius by 10 millimeters tall, around 77 watts per Kelvin. This is an impressive capability of the MP-1 to be able to measure these. We have very accurate results. If you're interested in seeing that demonstration, which is available in our channel for the MP-1. So I'm going to change camera angles and show you the setup for the bulk. I've already set the sample up. Of course, the sample setup is a little bit tedious. You want to make sure that you're placing those two white samples on top of each other, and that you're aligning everything up with the screw. It does take a moment to do. There are some templates you could build. If you had a standard size that was repeating and always the same size, you could build little templates to make that a little easier. These are just little square pieces of Macor ceramic. So I will disassemble that post measurement so you can see what that looks like. But this, the sensor size that will be recommended by the software I've already installed. If you want to see how the sensor connects to the adapter, I encourage you to watch some of our basic videos on the MP-1 to see that. Basically all of the capability are covered in a series of videos if you want to see. So we're trying to demonstrate the full capability of the MP-1, both transient plain source method and transient hot wire. So I'm going to go to the software and switch to the desktop. So here is, we've separated the software out into 2 applications. One is data acquisition, which controls the controller, the MP-1 controller, the multiple channels. What is multiple channels? It means that it can run multiple devices at the same time, and it schedules all the measurements and all the testing capabilities. So we don't just have multiple devices, we have a controller that can run them all, and software, smart, sophisticated software that recognizes them and automates all that as much as possible. So we try to build smart, intelligent instruments. That's our key. So right now, if you were to look at the MP-1, what's connected to it is a transient plain source temperature platform. We removed the temperature platform of the transient hot wire because we wanted to focus the visual attention on the transient plain source package. We have 2 room temperature sample holders connected to the MP-1, and those are self-identifying. So all the things, everything that you connect to the MP-1 is self-identifying so that it knows what is connected to each channel. So if you want to run an experiment, you go to create a new experiment. You point to where you want your data saved. We're going to select 3D source. I can run measurements in symmetric and asymmetric, which means 2-sided or single-sided. I can run anisotropy, which would be looking at 2 directions. I can run slab measurements, which would be looking at thin conductive sheets and thin films. We're going to run symmetric, bulk, or isotropic samples as a semi-infinite body. So it auto-detects itself as a controller and what's connected to it. So we're going to do room temperature testing with one of the 2 room temperature sample holders. I'm going to input the name. The height of the sample is 1.4. The radius is 2.5. The port I'm going to use is port 4. So we have the second sample holder connected to the back of the instrument. So there's 3 channels on the back. So sensor model. There is a manual way of selecting sensor to sample size. We've automated all that through our intelligent design. So the instruments come with no hidden steps of measurement. You can do everything manual, but we've made the instrument intelligent. That's really key. We've advanced the transient plain source several years through our automation and really making the instrument much more robust and capable through the hardware and the software design and the new testing capabilities to meet the needs of today. So sensor size, you just click the little what is the sensor size to use, and it shows 0.9 millimeters radius, which is what I have set up. If this sample was much larger, it would recommend a different size to meet the parameter requirements of the instrument. So go back to the height and the radius, and it'll select the same sensor. So we're going to check the sensor. That just means that verifies that you have this sensor selected. It also verifies the resistance, electrical, as a quick electrical measurement of resistance to verify that it's good. If you mouse over that, it tells you that resistance. Temperature is taken automatically from the adapters. So the MP-1, every sensor has the ability to read room temperature. So the adapters are smart and they know what's connected to them. ITPS, that's if you want to run and automate the selection of power and time. And it runs a continuous measurement. This is a proprietary technology that we've developed. It runs a continuous measurement based off of the dimensions that you input, and it gives you the output of power and time. We've already run that. It's about a 2-minute measurement. We've already run that, so we know it suggests, based off the available dimensions, 0.5 seconds for 30 milliwatts. So from here, I can verify that with a quick transient. Quick transient is meant only as a step towards making better measurements through your schedule function. The schedule function locks you into waiting a short delay between each measurement and allows the instrument to maximize its capability by scheduling each port fully. Then when you come back, you can look at your data through the thermal analysis software. So we'll let this run. There's no recording of drift. So typically when we're running measurements using the transient plane source in the MP-1, it will record drift for 40 seconds. But that's done when you schedule a measurement. Quick transients are meant as, do we meet our minimum parameter requirements through the ITPS function? It lets us check that to make sure. So once that is done, we'll do a quick review of it, make sure there's no highlights, meaning that we've met the minimum temperatures. So highlight if any of the temperature rise requirements or penetration depth or fitting requirements aren't met, it would tell you that in your review of your quick transient. So this is running a 0.5 second measurement. The MP-1, the full range of the MP-1 is 0.25, 0.5, 1 second. Variable test time is really important to measuring wide conductivity range. You have to be able to vary the time to stay within the dimensions of the sample. That's one of the fundamental assumptions of transient methods, is that you're keeping the heat within the dimensions of the sample. And you have to be able to vary time to be able to do that. So our quality indicators is what I was referring to. As you can see, they're all ideal. There's been no over penetration. You see our penetration. Why do we know what that is? Is because the instrument measures thermal diffusivity. So it's millimeters squared per second. So in a half a second, we stayed within the dimensions of the sample. So that's a quick check, which is a really confident way of proceeding. So by closing that, I can proceed to schedule a measurement. So I'm going to do 5 measurements. We only need a 5-minute delay. We're going to do 0.5 at 30 milliwatts. There is a default 10-minute delay before you start the first one. We can just make that 5 minutes and start. And then it brings up your schedule. This is our data acquisition review of your data that's in progress. And if you had multiple sensors or multiple measurements, they would just be in sequence here. You can see that our event log is recording the 5-minute countdown. So eventually this will generate all the data and we can look at it in the thermal analysis. To keep our demonstrations a little shorter, I've already run those measurements. So if we go to our analysis app, you could see the quick transient. It records the quick transient separately so that you can keep that a little bit better organized. And here is our Macor measurements. If I select those, I can look at the bulk results. So here is the thermal conductivity of that sample, 1.68, and there's our volumetric specific heat. If we want to see the fitting, we want to see our residuals have a nice random pattern. So that is the Macor measurements. Our NIST materials that we showed in a previous video. So this is the small format NIST electrolytic iron. You could see the thermal conductivity and thermal diffusivity. That the accepted value is around 77 watts per Kelvin, so it's quite good as well. So that's a review of both. But we fully demonstrate the one-dimensional module in another video if you want to review it. So as promised, I'm going to switch back to camera 2 and just disassemble this. Actually, I'm going to cancel that experiment if I'm going to disassemble it to show sample setup in reverse. So I'm just going to back off the knurled knob and lift up that. And as you can see, there's 2 samples on top of each other, and they are 5 millimeters by 5 millimeters. That concludes the, I'm sorry about the focus. That's too bad. Yeah, that concludes the review of the, you can see that I've canceled the measurement. That concludes the demonstration on small format bulk samples. If you have any questions, please get in touch with us, and we look forward to discussions with you.